As we think through all the considerations necessary to create a sampling design, we have to evaluate if they allow us to meet these requirements. First, do we have some kind of random sample? Without some concept of randomness, you cannot determine the probability of selection and therefore cannot make statistical inference about your population. Do we have a measure of interspersion within the sample? Your sampling units need to capture the variability of the target population. This helps ensure that we have a representative sample being drawn. Generally in natural resource management, we do this by proportionally sampling things along the edge of a population and within the interior of a population to account for any differences in the environment. And finally, we need to ensure that our samples are independent. You need to make sure that your plots are sufficiently spaced apart such that you are not remeasuring the same information or that your samples do not have autocorrelation between them. In natural resources, we generally accomplish this by using what's called sampling without replacement. Most often, when we talk about selecting sampling units in natural resource management, we are referring to selecting the location of a plot. When we are doing this, we must remember that an underlying assumption of inferential statistics is that any sampling design must ensure a known relative probability of each observation being selected and that the samples will be independent of the other selected units. This is the basis for a random sample. Although very similar, this differs from simple random sampling, which requires us to have a known equal probability for each sampling unit. Let us take a moment to refresh how these theories control our sampling distributions. First, the law of large numbers allows us to assume that by collecting enough samples, our sample mean will provide a good estimate of the population mean. And second, the central limit theorem allows us to assume that a large enough sample provides us a sampling distribution that will be approximately normal no matter what the population distribution looks like. Together, these theorems mean that even if we do not know the shape of our population distribution we are sampling from, we can draw inference about a population if we take enough samples to assume we are approximating the population mean and that the sampling distribution is normal in its shape. What if I had to tell you to shoot at a bullseye without knowing where the bullseye was? This is the case in sampling since the bullseye is unknown, meaning assessing the accuracy and precision of a statistical estimate is not very simple. The spread reflects the precision of the process, but the holes from the arrows only provide an estimate of the bullseye's accuracy. A confidence interval allows us to estimate the true value, or the bullseye, without knowing anything about the population distribution. This estimation process belongs to the techniques of inferential statistics, which help us determine how well our sample approximates the population. More simply, it allows us to describe the range of possible values an unknown population parameter could have. Beyond estimating the parameters we are interested in, we want to be able to assess how effective and efficient a sampling procedure is at estimating this parameter. Essentially, we want to know which procedure will get us the best answer for the least work. When we look at how efficiently a statistic provides an estimate of a population parameter, two things interact to control this process: the population variability and the sample size. When it comes down to actually designing a sample, our management objectives should tell us what we want to measure. However, knowing when to stop measuring is much harder and more important to determine. All of the sampling we conduct in natural resources needs to be statistically viable while remaining practical. when it comes to determining when to stop sampling, we have many possible options, including stopping when we have enough plots collected to provide whatever necessary precision we deem we need, or stopping simply because it's becoming inefficient to continue sampling, or stopping because we have answered our question, or because it's just becoming too expensive to continue sampling. Should we sample too much, we will have wasted time and money. If we sample too little, we will have high errors to deal with in our decision-making process. When it comes to our statistical approaches, preliminary data from simple random sampling can provide an estimate of variability and allow us to determine exactly how many plots we will need to achieve a desired precision level. The scale at which we choose to view a population at influences the level of variability or range of possible values that we would expect to find. If we look at this set of 5 1/10 acre plots, they reveal samples of 2, 2, 4, 0, and 4 trees respectively, giving us a sample mean of 24 trees per acre and a sample standard deviation of 16.7 trees per acre, overall showing us a fairly highly variable population. But what would happen if we sampled this same population at the same locations with a larger plot size? If we look at the plots now using 5 1/5 acre plots, we now have samples of 4, 5, 7, 2, and 5 respectively, giving us a mean of 23 trees per acre and a standard deviation of 9.1 trees per acre. While we see almost no change in the sample means, there is a significant decrease in the sample standard deviation at the larger plot size. Using this larger plot size reduces the odds of us having extreme values within the sample. The reason this can be an important consideration in sample size determination is that we may want to use one plot size in our sampling design, but may have some preliminary data from another plot size that we need to use in determining our population variability. Although it will only provide a rough way of scaling our plot size, we can use this formula to scale the variance of our original plot size in the preliminary data against the plot size we want to use in our sampling design to get an estimate of variance at the scale we want it at. The basic underpinning of stratified random sampling is that we take advantage of prior knowledge about the population to improve our sampling design. Within this system, we seek to improve our precision by optimally allocating our sampling efforts into areas where we have homogeneous values. By taking advantage of our knowledge about the population, we are able to divide the population into strata of expected subpopulations, or strata with a known range of potential values for sampling. When doing this, strata must not overlap, and all areas of interest must be included. In the big picture, the only drawback to stratification is the increased effort needed for the bookkeeping of the data and computation of the statistics. There are 3 sample allocation approaches we will look at. The first approach is equal allocation, where the sample size is set equally for each strata. The calculation for this process is fairly simple, where we say that the number of samples in each strata is equal to the total number of availables divided by the number of strata. The second approach to sample allocation is proportional allocation, when the number of plots per strata is proportional to the area of the strata. This process makes the sampling intensity equal for all strata, meaning that we sample the same proportion of area in each strata. The final approach to allocation is called optimal or Nyman allocation. in which the available plots are allocated by an equation that ensures that the standard error is minimized. In this case, the number of plots that a strata receives is proportional to its area-weighted standard deviation. When it comes down to it, though, in natural resource management, there are rarely a need to do anything other than proportional allocation. It has been said that the simplicity and self-weighting feature of proportional allocation are probably worth a 10 to 20% increase in variance. It is important to remember that the allocation process is simply a guide to determining how many samples each strata should receive. We must then use our judgment and determine if this allocation is the best way to meet our sampling requirements.